Hi, my name is Ryan Alcantara. I'm from the University of Colorado, and I'm going to talk to you today about curve sprinting with a split toe running specific prosthesis. I want to start off by thanking Phil Composites for partially funding the study and producing and providing the prosthesis we tested. For track events longer than 100 meters, more than half the races run along the curve. And curve running velocity can be described as a function of runner's mass M, curve radius R, and centripetal force production FC. And for an individual using a running specific prosthesis, centripetal force production on the curve can be challenging because the prosthesis is designed for linear running. It's very torsionally stiff in the frontal plane. But Phil Composites has produced a running specific prosthesis where the distal end is cut in the anterior posterior direction. So here we have an example of the kind of a cross section of the distal end of the prosthesis, where the distal parts, there's two of them now, can move somewhat independently. In theory, this increases traction on the curve, which would affect centripetal force production and overall sprinting performance. And so we compared the sprint performance of using the split prosthesis to a traditional solid prosthesis of the same shape, material, stiffness, and mass. And we compared these two prostheses across two curve conditions, a curve with a radius of 17.2 meters and a curve with a radius of 36.5 meters. And these represent lane one of a 200 and 400 meter track, respectively. We used force plates to measure centripetal force and optical motion capture cameras to monitor running velocity, sprinting velocity. We hypothesized that the split prosthesis would increase sprint performance velocity compared to the solid, and that it would increase centripetal force production compared to the solid prosthesis on the curve. We did compare these two prostheses on a straightaway. I'm not going to present those results, but essentially there was no difference in velocity or centripetal force on the straightaway between the two prostheses. Here are the curve sprinting results. On the y-axis is sprinting velocity, and the x-axis is the comparison between the split and solid prostheses for each participant in this pilot study. The colors denote the two curve conditions that I described earlier. And what we see if we look just quickly is that there's an offset between the 17.2 meter curve times or speeds and the 36.5 meter speeds. And overall, we quantify this as a 0.31 meters per second decrease in sprinting velocity when on the smaller radius curve. And this agrees with prior research, which has found that as curve radius decreases, so does maximal sprinting velocity. If we compare the two prostheses, overall, the split prosthesis resulted in sprinting velocities that were 0.13 meters per second faster than the solid. Although, if you look at the individual participants here, we see that there's a range of benefits or varying degrees of benefits of the split prosthesis. And that leads me to the next point here, which is that there may be some interaction between curve radius and the velocity benefit that we observed in the split prosthesis. If you take subject 3, for example, we see that the slope of the line, representing the difference between the solid and split prosthesis sprinting velocities, the slope of the line for the blue 17.2 meter condition is steeper than for the 36.5 meter condition. So if we try to relate this back to a track and field event, someone using the split prosthesis in lane 1 might see an increased benefit compared to someone using the split prosthesis in lane 8. If we look at centripetal force production, here we have on the y-axis stance average centripetal force. We see that the individuals that saw speed or velocity increases also saw centripetal force production increases. That would be subjects 2 and 3 primarily, with subject 1 not seeing much of an overall change, similar to with their sprinting velocity results. Overall, the split toe prosthesis resulted in maximal effort sprinting speeds that were 0.13 meters per second faster than the solid prosthesis. However, like I described earlier, there may be some interaction between curve radius and this velocity effect. If we try to extrapolate these maximal effort velocity differences to a 400 meter race, the curves of a 400 meter race, we would save about a half a second over the course of a Paralympic 400 meter event. This would be the difference in the 2016 Rio Olympics, at least, between a bronze and a gold medal. But more work is needed to confirm the speed effect and identify other underlying mechanisms. But there's an opportunity to test some very simple but potentially effective prosthesis designs that could improve sprinting performance overall.